All right, good morning. How's everyone doing?
Doing well, Nick. How are you doing?
Doing well too, thanks. All right, let's start with questions. Any questions on homework 8? Can't remove the first underscore from a line. All right, let's see. That's interesting. I don't know why Zoom said that message went to all panelists. I don't know what a panelist is, but I'm not going to worry about it. Let's look at some said stuff. So there's a line with some extra stuff in the beginning. So if I echo that and I pipe it into sed, if I want to remove a leading underscore, I can say caret for the first piece of the line and then underscore, and I can say do that, replace it with nothing. That would take out the first underscore. If I want to remove multiple underscores, I can say beginning of line underscore followed by a star, which means any immediate succession of 0 or more underscores. So that would take out all of those underscores in the start. And then if I want to actually remove that from line, I can do my usual trick of take the result of that echo statement, right, which will be this, put it in back quotes, and then assign that to line. And so now if I look at $line, it looks like that. So if that's my value of line, right, that'll take out those leading ones. And then if I want to take out the trailing ones, I can search for underscore star, which is any succession of underscores, followed by $, which is the end of the line, and replace that with nothing. So that would take out the ones on the end, but leave the ones in the middle. And if I put all of that in back quotes, then I've actually removed it from that variable. Does that help?
Hey, Professor.
Hey.
Are you in the middle of something?
Nope, think we just finished.
Oh, okay. Cool. Oh, you just finished, like, a class, right?
I mean, we just finished talking about the previous question. So this is a good point for a new question.
Okay, cool. I guess, my question is, like, so I'm trying to read the homework 008 testing phase.
Mm-hmm.
But when I try to type in the command that you say, it says that it can't find the directory. So yeah. When I go, let me pull up chat and try to copy paste what I do.
Yeah, that would be good. Let me put my.
Okay. Here we go.
So there is no file called test0.in in your current directory, apparently.
So how would I access those test files? Because I do know copy/homework008 tests, but I don't.
Good.
know
Do it exactly the same way. So I've got it typed in a console window right now. So just do main.sh less than, and then say /temp/homework008 tests/test0.in.
Oh, cool. I was doing the directory after the file, so this makes sense.
All right.
Test0.in. Oh yeah, main.sh. There we go. Message. Okay, thank you. That'll help me
Okay.
test my file.
And then if you want, right, pipe the output into sort-n and then redirect that into, but don't redirect it into /temp/homework8/test0.out.in. Just redirect it into your own output file in your own directory, test0.out.
Okay.
Because it won't let you write the one in temp. Cool. Other questions? And I turned off your mic, but if you want to talk, turn it back on.
Oh, sorry. I actually do have another question.
Okay, go for it.
So, this is what happens when I run the command, but the output looks fine. The output looks fine, but it says this every single time. Well, every single line, I think.
Key command not found. Key command not found. Key command not found. Okay, can you paste line 63 from your file?
Yes. Yeah, main.sh. Line 63.
And no, you do not have to store it in the script. In fact, there's no way to store it in the script unless you use an external file as a temporary, or you put things in memory, which limits the amount of data you can process. So no, do not store it inside the script unless you really feel like you want to for some reason. But I suggested taking the output from your script and running that through sort just for the sake of comparing it to the sample outputs, which I also ran through sort.
Oh, I get it. I get what went wrong. The equal sign is off.
Ah, yes, yes.
There we go.
Yeah, spaces and equal signs are always a gotcha with Bash.
Okay, I'm gonna mute myself again.
Okay, cool. So there's this this rubber duck theory of computer science programming, which is and you can actually find these things online, I think, which is when you're stuck on a problem, explain it to a little rubber ducky, right, or a teddy bear or whatever is handy. And the process of verbalizing a problem and showing it to someone can often help you see it. And so there's a lot of times students will come to me and start telling me what's going on with their code, and partway through they're like, oh, wait a minute, I got an idea. And they go off and try something, and it totally works. So yeah, the debug duck. So, and that doesn't mean I don't want you to come to me and debug with me. That's what I want you to do. But I'm just saying, in general, that's another resource that can be helpful, especially late at night or something. If you're stuck, just try verbalizing it to an imaginary audience or person or programming partner or something. And sometimes that can help you see something you didn't see before. All right, good. Other questions? Quick way to check if you succeeded that your file is the same as the example. Cool, yeah, so you can use the compare program. Oh, good job. Someone got their program basically done. Awesome. So yeah, the other thing you can do is difference. So let's let's go ahead and run my script on a test file. Right, so there's my output, and here's the output that I should have gotten, and I can see immediately that they're not the same, right? Because I forgot to sort my output. But you know, if I want to know if these things are different, I can just compare output with test0.out, and I'll get a bunch of output if there's any differences, basically saying, you know, in the first file it found these two lines, whereas in the second file it found this line as without that following line after it. And then it found this in the second file followed by this, whereas in the first file it just found this. So there's some differences there. So you know, my script should work correctly, so I'm just going to run this, and I'm going to pipe it into sort-n and put that into output. And now if I do this difference, I get nothing on my display. That tells me there's no differences between the files. And so diff is another file you can use to, another program you can use to compare two files. And that works great, you know, with these really big test cases. And this one takes quite a while to run. But you don't want to go through this output and try to compare it line by line with the intended output. Yeah, diff is a standard part of Linux. Pretty much every Linux system will have that. And it's, you know, it's just a C program. And it will let you do lots of different things, including give you a normal diff. Or you can do it line by line. That works too. You can do this on binary files that you wouldn't be able to look at the contents of, and it won't show you the differences, but it will tell you if there are differences or not. Diff also generates this output, right, with these tags in here. You can use this with a program called patch, and you can basically take this output, run it into patch along with a copy of this file, and it will change it to look exactly like that file. And this is one way you can roll out changes to programs, run a difference, send it out to people, and say apply this patch. So yeah, so compare it to temp homework 8 tests test0.out. Yep. Yeah, I'm chewing up 8% of the CPU. That's the homework 8 script running in the other window. Oh, just finished. That's gone. So there's our sorted output, Wuthering Heights. And you can run a difference, and there's no differences. If you get to that stage with all 5 of your tests, you probably got 100 on the assignment. As long as, you know, you put in comments and indented your code and did all that other stuff. But as far as the behavior of the program, if it works on those 5 cases, you're pretty close to guaranteed your code is you know, functioning perfectly. All right, good. Other questions? Yeah, test 4 does take a while. There's a command called time, which you can put in front of a command. And it will run the command, but when the command is finished, it will give you some statistics on the execution, how much CPU time it took, how much system time, how much elapsed time. And even though this is taking a long time to run, you know, if you look at top, it's only getting, you know, a few percent of the CPU. So there's another version that's running that's getting 4% of the CPU. It takes a long time, but it's not really crunching, assembly language instructions for most of that time. Most of what it's doing is input output, right? Or things like that. So the CPU time we see from this will probably be quite a bit less than the actual elapsed time. I don't know if we can interrupt and still get a result. Yeah, we can. So let me just kill mine. So so the real time was 1 minute and 8 seconds. The actual CPU time was 0.8 seconds, and the system time was 1 second. So it used 2 seconds out of 68. So Bash is not the most efficient environment in the world to be running code, right? If you were trying to search for new prime numbers, you would probably not do it with a Bash script, right? Because it's just a lot of overhead, because Bash is interpreted. And Bash is loosely typed, and there's lots of layers between the Bash code and the underlying CPU memory. But the trade-off for that is that it's a very sort of comfortable language to develop in, and that can be worth it in most cases. What's your most efficient choice if you wanted to search for new prime numbers or something? What language or environment would you develop in? If you were going for just like blazing speed.
I think Python, maybe?
Python's an option. What else? C. Python is I don't know a lot about the internals, but at a first order, Python is still interpreted. Your code's being interpreted as it executes. There's probably some compilation phase to that also. But C is a pretty good bet. Assembly, there's no way that you can write a program in C that's going to run faster than something in assembly, right? Assuming you're a good assembly language programmer. Or machine code, because that's what all that stuff compiles down to, right? So you could always replicate the assembly language or machine language that the C compiler gives you. But C is really pretty good. The mapping from C to assembly is very direct. And if you're careful with just a few things, like watching out for bad memory situations, things like that, you can probably get pretty close to assembly language efficiency in C for, a small problem. And that's in some ways, part of what C's purpose is to be like high-level assembly language. Java would probably not be the way to go, because Java is also interpreted. But the difference between these things is getting smaller over time. And, if you have a 3 gigahertz CPU and you're doing something that's going to take 1 million cycles, who cares if you do it in Bash or Java or Python or C or assembly language? But if you're going to run something that takes 6 weeks to run, and you really care about speed, probably do it in C. Except my jobs are in Java, because I don't have time to write them in C. All right, good. More questions? All right, so I think I mentioned it yesterday, but I just wanted to make sure I mentioned it. Really nice job on homework 7. Everybody did a really great job with writing their code for that, coming up with good designs and really nice presentations. So I was really happy with the results everyone got, and with how they were presented. I still need to put grades in, but I think everybody got 100. So that's easy. So yeah, nice work with the previous homework. Somebody said most of my lines are different. Yeah, that can happen. So if you're getting differences, here's what you do. Go into VI and take a close look at your file. So let's look at test0.in. If you say :set list, it will throw a little $sign at the end of each line, so you can see exactly what each line looks like. This first line starts with the letter A, ends with a period, followed by a few spaces. Now if you do this on your output, you'll also be able to see if there's spaces in the beginning or the end. And chances are, if your lines look the same, but they're coming out different when you run diff, you've probably got trailing spaces or something pretty minor like that. And then you can go back in and you can add some echoes to your code. And you know, when you have a phrase, for example, you're about to use, just go ahead and echo it. But remember, when you echo, throw some delimiters on. I usually use angle brackets, but you can use whatever. Right? And this will say echo equals angle bracket, and then if there's spaces at the end of this, I'll see a bunch of spaces before I get to that closing angle bracket. This won't help you if you have weird characters like, you know, a Control-C or Control-F sitting in the middle. But this, you know, we're mostly worried about deleting trailing spaces. This will let you see those. Is there a big performance between C Shell and Bash? I don't know. Unless somebody, you know, deliberately wrote one or the other with an eye towards performance, I would guess they're pretty comparable, but I don't know. I have no experience with that. To me, they're both, you know, slow enough that I wouldn't do something serious computational-wise with them, but fast enough that I don't hesitate to use them for, you know, pretty much anything on the day-to-day basis. And I used to like C Shell a lot. It has a much more C-like syntax. So this is CSH. It's called the C Shell. It has a C-like syntax for things like loops and conditionals and stuff like that, which was nice. And Bash, you know, has all the quirky stuff with the bracket space -LT. But Bash right now seems to be the more popular shell. This changes over time. But since it's the one that people are more likely to encounter, I bit the bullet a while ago and just sort of threw myself into Bash so I could like work with it and teach it for this course. But you know, once you know one shell, you know pretty much all of them. You have to figure out the syntax differences and so on, but that's not a big deal. It's just kind of more of the same. All right, what else? All right, so let's talk about processes. And this is kind of a bit of a general topic. I just want to sort of look at the idea of what processes are and what they are in Linux. And today, look at this from the perspective of working in Bash. Looking at processes, interacting with them, controlling them. And then I want to move towards tomorrow or Friday, talking about how we deal with processes in C. How do we actually create processes, signal them, kill them, connect them, things like that, from C code. And this is something that, you know, you'll encounter again in other courses, but just kind of give a first view of it if you haven't looked at it before. But let's start with Bash. So I'm gonna do this on my own server, so we don't look at too many usernames. So I'm on a Linux machine. Okay, yeah, kill-9-1. That's a good thing to try. figure out what init does. But don't do that. So I'm on a Linux machine. Okay, this is running on a laptop. And usually when we interact with our system, we're kind of thinking of this as, bash, right? And a lot of people use the term bash and the term Linux interchangeably. Bash is really one program, right? And there's this one program running right now which has printed out, bracket 2014 and is waiting for me to type. And when I say, date and I hit enter, it magically prints out the date and time. That is really the only view that I'm usually worried about of Linux, right? I want to be able to look at files, edit files, compile them, run them, things like that. But in reality, right, this is just one process, one task running out of a few hundred things that are happening on my machine. So a good first order command to know is top. Top will show you information about what's going on your system right now from the perspective of what's taking the most CPU time. So a bunch of information on here. So current time, so 11:27. How long the system has been up. So it's been up just over a day because I rebooted because my camera was doing weird things. 5 users on the system, right? So this is my own machine. Load average is a measure of how heavily loaded the CPU is. And ideally, these numbers should be really small. If they're up around 2 or 3, there's something going on the system. And if you don't know of anything that's running on the system, there's something running you're not aware of. If these get up to like 7 or 8 or 10, I'm probably experiencing some slowdown. And I've either got something, very deliberately CPU bound running on my system, or, maybe I've got a runaway process somewhere. Tasks, 328 total. There's 300 plus things happening on this machine right now. Even though I'm only doing one thing, I'm running the top command, right? But there's hundreds of things happening on my system right now. I have 2 processes running. I have 254 sleeping. So most of the jobs on a system are not actually executing commands. They've executed a few commands, well, a bunch of commands, and now they're in a state where they're basically saying, wake me up when something interesting happens. Okay, if you've done Engineering 270, what we're talking about is interrupts. Remember, we wrote some code where we wanted a program that would just kind of hang out until you pushed a button, and then it would increment a file register and output that to the display. Well, that hang out until someone pushes a button was usually just an infinite loop. But infinite loops are expensive. They take a lot of CPU time. So most processes don't spend their time in infinite loops. They let somebody know what they're interested in, and then they go to sleep. It's a different state of a process. And when a process is sleeping, it doesn't take CPU time. It's I don't want to say literally asleep, but if you were to draw the analogy, it's literally asleep. But it's left an alert, right? Message to the front desk saying, hey, when somebody hits the enter key, wake me up. So now you can hang out and you can go make breakfast, you come back, you type something in, you hit the enter key, and the operating system sees that and says, oh, wait a minute, I had someone who wanted to know about that, and it wakes up that process and says, hey, that thing you wanted to know about just happened. And then the process, which was maybe in the middle of an fget call, will execute some instructions to read those characters and so on and so forth. So most things are sleeping. Okay, and there's a state column here, S, and if that says S, that's sleeping. We've got a few things running. Okay, Xorg is managing my display. So most displays are using something called X Windows or X11. Xorg is running my display. GUVC View is my document camera, right? And that's taking 87% of the CPU time. Xorg's taking 85. Simple Screen Recorder is taking half a CPU. That's the thing that's recording the desktop, so that I can post it. Zoom is taking half of a CPU, that's zoom, right? Here's my other GUVC view, which is my other camera up here, which I've got the lens cap closed on, and so on. So, you know, 300% of the CPU across just a few processes. I have 4 cores, so I can end up with these CPUs adding up to 400%. None of them are taking a lot of memory. And I've got 16 or 32 gig memory on this machine, so memory's not an issue. But it's this CPU activity that's driving this load average up. And I think this is current, 5 second, and 1 minute, or 1 minute and 5 minute, or something like that. It's current and then some longer averages of load. All right, so lots of processes out there. Let's take a look at some of these in detail. So I'm going to say PS. PS shows me process information. And when I say PS, it gives me 2 lines of output. I completely forgot to tag my previous lecture, so I'll try to put some tags in here. So PS shows me the current processes associated with this bash session. And there's 2 processes. One of them is the command bash. Well, that's my interactive session right here. The other one is this PS command, which is what I typed right there. This is the total amount of CPU time this command has taken, and it's pretty much 0. Bash does not take a lot of CPU time. There's a column labeled TTY, that's a teletypewriter, and it wants to know which teletypewriter is this command run from. Okay, so go back into, the 60s, and you had a CPU sitting inside, a room full of equipment, and wires coming out of it going to a bunch of terminals. And people would sit at a terminal and they would type, right? Well, those terminals had different IDs associated with them, TTY 1, 2, 3, 4. This would tell you which teletypewriter the person was on. We don't have that going on my laptop, right? There's no air-conditioned room with wires coming out of it. So this is a pseudo terminal, PTS. And all the terminals associated with processes on bash are these pseudo terminals, right? They're not actually physical terminals the way they would be in the older days. Let me see if I can find a quick picture of a teletypewriter. There's a classic. All right, so to me, this is the classic. That's a TTY. Right? So you would type here, and it was like a typewriter, and there was this, scrolling paper up there, and there was also a tape punch on the side. And you could code things that you were typing into this tape punch, and then that could be read by a tape reader. And this was awesome. It had a mechanical bell hidden back here, and if you did a Control-G ASCII code 7, this bell would actually ring, and a little metal thing would get actuated with a solenoid, and it would clang against this bell, and it would make a dinging sound, and that was awesome to write things that would knock out interesting beats with that, and so on and so forth. So that's a TTY, right? That's really what this column represents. Except that we don't have those anymore, so they're pseudo terminals. All right, so if we do a PS-F, that will give us a little more information. And so it shows us the full command that was run. So bash is the name of the command, but it was actually /bin/bash. And PS-F was the PS command that was executed right here. It still shows how much CPU time. It shows the terminal location. It shows the start time. So when did this command start executing? Well, bash started at 11:02. That was the beginning of the class. ps-f was 11:35. That was just now. There's a user ID associated with it. So the user ID who owns these processes is Nick. That's me. Okay, it's a numeric code, but the ps command translates it into a readable name. If you want to know what those codes are, you can look at /etc/password, and you can do this on the Linux machine if you want. It's an open file. It lists usernames, passwords, and then a user ID. So if I look for Nick in here, you can see there's Nick. My user ID is 1000. This will also tell you the person's home directory, what shell they're running, and some other information. And this used to be where the password was stored. Well, we don't do that anymore. We store the passwords in a separate file. But the encrypted password would normally be stored right here. All right, so that's what the user ID is. It's the interpretive value of the numeric user ID. Let's see, what code were TTY machines using? So these were really just dumb terminals. They were putty, basically. You could type on the keys, and that information, would either go to a paper tape, or, in some models, it would go through wires in the back into a computer. And if that computer was running, an operating system, you could be typing to the operating system, or if it was executing a command, that would be input to the command, and so on and so forth. And then whatever came back from those wires would get printed on the printer side. But they were really just, input-output to a CPU, which could be doing any of a number of things. Could be running, any sort of program. But you could code up a paper tape with the right timing of spaces and bells, and then if you took that tape and ran it through another machine and had it replay it, you could get it to, knock out little tunes and stuff. So no, CPUs did not have keyboards. Typically the CPU is just a big box with wires coming out of the back, and some of those wires would go to terminals that would talk to it. Probably one of those would go to a console terminal that would be in the same room. That would be the main interface to the computer, but that generally wasn't something that people used, and certainly not users who wanted to compile their Fortran programs or whatever. They would either use, a keyboard that was attached outside, or more likely, they would punch up their program on tape or on a deck of cards, hand that to an operator would run that through the system. And this was a painful way to do development, right? When I started taking programming classes, this was the state of the art. So well, not exactly, but this was what was state of the art for the school. You would type up your program on a bunch of cards. You'd hand those cards to an operator. They would wait till the CPU was free, and they would run the cards into it. And the CPU would run, they would generate some printout, and then they would take the printout and they'd put it in a cubby hole with your last name initial on it. And you just go back every now and then and look to see if your printout was there, and if it was, you'd get your printout, and that would have your output. And you'd say, oh, I forgot a semicolon, right? And you'd change the deck of cards and go through the whole process again. And, it could be a 2-hour development cycle to edit, compile, and test. If you typed ls or something into a teleprinter, would it physically print out stuff in your directory? So on a teletypewriter, no screens. It would physically print it. But again, for a lot of these systems, there was no such thing as typing a command ls. Really, all you were doing was generating a deck of cards or a strip of paper tape. But yeah, if you had direct access to the operating system, it would print out the results of, ls or dir or things like that. And that's kind of nice, because it meant that, you always had a physical copy of what you had been doing, and you could take it off with you to lunch or dinner and, get a highlighter and debug your code while you were eating. But, CRTs are so much nicer. All right, so the most interesting part of this display is this new column, PPID. So PID is the process ID. Okay, process ID identifies the process. Okay, so it's you know, there might be a lot of things called /bin/bash, but this particular one is also identified by this number. So it's like your driver's license number, right? There might be different people with the same name, but this is unique. So bash, this interactive session I'm running, is process ID 593. The PS command was process ID 4093. And if I do this again, oh, not that. If I do this again, bash is still process ID 593, but the PS has a different ID. It was 4093, now it's 4999. And if I do this again, now it's 5001, 2, 3, 4, right? So each time I do PS, I'm creating a new process. And it's getting a new process ID. And you know, these are handed out sequentially, so if I'm fast, I'll pick up the next process ID. But if other stuff is happening, like if I were to close out this window over here and open up a new tab and who knows what else, right? Lots of things just happened. And so now PS has this process ID 5024. So the parent process ID says, where did this process come from? So the PS command, process ID 5024, where did it come from? Its parent was process 593. That's the bash shell. Well, that makes sense, because what happened to cause this PS command to come into existence? In my bash shell, I typed ps-f. All right, so this is a hierarchy of processes. The PS command was created by the bash shell. Where did the bash shell come from? So if I do a ps-elf, that will show me a full list of every process on the system. And if I run that, I got all kinds of stuff out here. All right, so let's go back to just looking at this. My bash shell is process 593. The parent is 587. Let's see what process 587 is. So I'm going to do my ps-elf, and I'm going to search for 587. And I get 3 lines back. So let me make this a little bigger. Let me make this a little smaller. I get 3 lines back. And yeah, you can see every process on the system, even if they're not owned by you. So if you do this on the Linux machine, you can see every process everybody is running. That's totally open. So here's one line from my PS that mentions a 587. That's because I said grep 587. Okay, so that's not really what I'm interested in. Here's another line that mentions 587. Well, that's because, you know, something in this column had a 587. I'm not interested in that. Here's the bash line. Okay, there's my bash process. It's ID 593. Its parent is 587. We already saw that. Here's what we're looking for. This is the command whose process ID is 587. And that's a command called user bin console. And console is the name of the terminal program that I run on Linux. And if you can see at the top here, it's really tiny. It says nic:/bash-console. That's the name of the program. And it's just, you know, it's just a part of well, it's not in there. But it's just a program. And you run it and it opens up a terminal window for you. Sometimes they have help available. Right? So console is the thing that created the bash program. And I've set things up so when I hit Control-Alt-T, it runs the console command and asks it to start running bash. And that creates a new shell. Okay, console's parent ID is 6925. Let's see who creates that. Well, 6925 is this process right here, which is called XF settings D. All right. So when you have a process that ends with a D, there's a good chance it's what's called a daemon. which is basically a server program, something you can send requests to and it will take action for you. And this is the daemon that apparently is created to allow me to do GUI type things on my system. So process 1 is the init process. It's the first process that's created when the system boots, when Linux boots. And it created this XF settings daemon. And 6925 is the parent of a number of processes. It's the parent of this console process. It's also the parent of Thunderbird, that's my mail client. It's the parent of this process, which is running my browser. It's the process of this client, which was an application finder, and it's the process of another console session. Now, if I do a ps-u nick, I can see all the processes that are associated with user ID nick. If I put an F in the front, I can get a full listing, right? There's all the process information for everything owned by Nick. And there's a lot of processes out there. And yeah, this is a bit of a security thing to be aware of. If I run a command with some arguments on it, anybody can see those arguments. Right? You know, I'll edit a file called password is haha, and somebody else comes along and does a PS, and this is harder to find than I thought. There, right there, I can see the person's editing a file with this name. So a lot of the stuff is like openly available. All right. So what do I have running on the system? I have a VI process running in the other window. I have my grep VI. That's this command right here. I used a pipe to connect commands together, right? I have my camera running on my document camera. I have a camera running on this little window view camera, and other stuff like that. Are there versions of Linux where these types of things don't exist? I'm not sure. I mean, there's lots of different versions of Linux that are made with an eye towards security. I don't know if preventing people from being able to see, you know, this kind of information is something that can be locked down easily, without radically changing the nature of the operating system. I don't know, but yeah, there are versions of Linux that are supposed to be more secure. Although I would say I don't know if this is necessarily a security vulnerability, as long as people are aware of it. But remember, you know, Linux, everything is a file, and so if you look in /dev, right, this is the essence of the system. All these things are files, and this you know, FD, that's a floppy disk drive, and there's a processes in here. And kind of the design of Linux is, you know, everything's a file, everything's accessed through the same mechanism. So a lot of this stuff is more or less out of necessity visible. All right, wow, we are out of time. That went fast. So tomorrow I want to look at some more particular process commands. I want to look at executing jobs, putting them in the background, running them in the foreground, moving back and forth, sending signals to them, including how to kill them, and then take a look at how we do that in C. All right, cool. I will see you next time. Thanks.